Hey everybody, welcome to tutorial 25. In the next two videos, we'll talk about granular synthesis, which refers to a family of techniques that involve chopping up a sound into short segments called grains and reassembling them to create a new and possibly very different sound. In this video, I'll focus on granulating an audio file that's been recorded and stored in a buffer ahead of time, and in the next video, I'll show you my approach for doing real-time granulation on a live signal. What I hope to demonstrate is that granular synthesis is a very powerful and flexible tool, capable of producing many different results, including rhythmic patterns, complex drones, pitch shifting, and time-stretching effects, and lots of other bizarre and exciting transformations. The default SuperCollider library has a small but robust core collection of granular UGens, which you can find in the help documentation under Browse, UGens, Generators, and then at the top, the granular category. Some of these, like grain FM and grain sine, synthesize an audio signal and then granulate it. Grain in will granulate an arbitrary audio signal. So this might be coming from a microphone, an internal audio bus, or it could just be the output of another UGen. And then the other granulators, which are GrainBuf, T-grains, and Warp1, operate on an audio signal stored in a buffer. Ultimately, these UGens are all granulators, so naturally they're all kind of similar in some ways, but unique and interesting in their own ways. So it's definitely worth experimenting and seeing which ones are most exciting to you. Personally, I found that about 99% of the time, GrainBuf does everything I need it to do. So that's the UGen I'm going to focus on. So first we boot the server, and I'm also going to open a few different GUI tools to help us better visualize what's going on. And then we need to go find some audio and load it into a buffer. Now I've gone ahead and grabbed this sample of me talking about my brain exploding back in tutorial 21.
It just completely broke my brain. I had no idea what I was hearing or that sounds like this could exist.
I think spoken text is one of the more interesting things to granulate because it's often rhythmically and spectrally interesting to begin with. It has this extra layer of language and meaning that synthesized sound doesn't usually have. Now, of course, you can granulate anything you want, but the main reason I've chosen this sound is because I think spoken text makes for a particularly clear and instructive demonstration of granular synthesis and really helps explain the nuances of how it works. So let's get started and build a simple function with GrainBuf. We're going to talk our way through these arguments, set up some simple sound examples as we go in order to demonstrate how the arguments behave and interact with one another, and finish with a slightly more complex and creative example. The first argument is the number of channels that you want GrainBuf to output. The default is 1. This produces a monophonic output signal. This is pretty boring. And in most cases, you'll probably want to put 2 for stereo output. We'll leave it at 1 for now and come back to it. Next argument is trigger. And whenever this value undergoes a non-positive to positive transition, that's GrainBuf's cue to generate a grain. This can technically be any signal, but there are two UGens in particular that come to mind that I think make a lot of sense to use here, and they are impulse and dust. Impulse has a frequency argument and outputs a periodic stream of pulses at that frequency, so this would be exactly 10 grains per second. Dust, on the other hand, outputs pulses at random intervals but maintains a relatively constant density of pulses per second. So this would give us a cluster of approximately 10 grains per second, maybe a little more or less. We'll use impulse for now and come back to this later. Next is dur, which controls the duration of individual grains measured in seconds. Like the trigger argument, this can also be a signal, but to keep it simple, for now we'll fix it at 0.09 seconds. Fourth argument, sound buff, is the buff num of the buffer containing the audio that we want to granulate. And we've named that buffer B, so b.buffnum would work, or to keep it short, we can just put B. Next is rate. This is a ratio corresponding to the playback speed of each grain, and this behaves like the rate argument in playbuf, which we saw in tutorial 8. 1 is no change in pitch, 2 is an octave up, 0.5 is an octave down. For right now, we'll just put 1. After rate is pause, which is short for playback position. This corresponds to the location in the buffer where each grain will start, and this is on a normalized scale, which means 0 is the beginning of the file and 1 is the end. I'm going to use a value of 0.2. So all grains will be extracted starting at the same spot, exactly 1/5 of the way through the original file. Now, this should make sound if we stop here, but for the sake of completeness, I want to finish off the rest of these arguments. So next is interpolation, which determines the type of sample interpolation if there's a change in playback speed. 1 means no interpolation, 2 is linear, and 4 is cubic. The default is linear, which I think is fine for most applications, so we'll put 2. Come back to this later in the video. Next is pan position. If you provided 1 for the number of channels here at the top, then GrainBuf ignores this argument. But if you provide 2 for number of channels, then the pan argument is interpreted exactly as it is with pan 2, where 1 is hard right, -1 is hard left, 0 is in the center. After pan is env-buff-num. Like soundbuff, this should refer to a buffer that contains the shape of an amplitude envelope, and this envelope gets applied to each grain. The default is -1, which means GrainBuf will use a built-in Hanning window, which has a bell curve shape that looks like this. So by default, every grain has a smooth fade in and fade out, reaching peak amplitude right in the middle, and this helps avoid clicks and discontinuities in the output signal from GrainBuf. So for now, the built-in Hanning envelope is fine, and I'll show you how to use custom grain envelopes later on. The next argument is max grains. This is simply the maximum number of overlapping grains that can exist at any moment. The default is 512, which is fairly generous. I don't think I've ever needed to increase or decrease it. However, keep in mind that this value can't be dynamically changed as the sound is running. So in other words, this is a fixed value at the moment when the sound begins. The last 2 arguments are mul and add. These are included in basically every UGen. We use them to mathematically scale and shift the output waveform, and we're just going to ignore them like we usually do. Okay, let's play it. And just hit Command period to stop that. Nearly all parameters are constant, so as expected, we get a stream of 10 identical grains per second, each one 90 milliseconds long, all pan center, etc. Now, if you're following along and you don't hear any sound when you run this code, I can think of 2 reasons that might be happening. One thing to consider is that in your audio file, whatever it happens to be, there might just be 90 milliseconds of silence starting 1/5 of the way through, in which case you're creating grains that contain nothing. So first thing to try is nudge this position value around and see if something pops out. If you still don't hear sound, then I can almost guarantee the problem is that you loaded a stereo file into your buffer. And in the help file for GrainBuf, it says soundbuff must be a buffer holding a mono audio signal. And I believe this is a requirement for T grains and warp 1 as well. So using num channels, we can see that my buffer is monophonic, so that's good. But let's see what would have happened if I'd accidentally loaded a stereo file instead. So here is the same sound, but it's in 2 identical channels instead of just 1.
It just completely broke my brain. I had no...
And now if we reevaluate this GrainBuf function, we get nothing. On the node tree, we can see that we've created a synth, and it's sitting right there in the default group, but nothing in the output meters, nothing on the scope. At the time of making this video, what the help file doesn't tell you is that if you try to granulate a multi-channel buffer, GrainBuf will fail silently. No errors, no warnings. So if you're not expecting it, this can become a brutally difficult problem to diagnose. Now, before you go jump into your favorite audio editor and start mixing all your files down to mono, there's a much better option, which is to use buffer.readChannel. We saw this back in tutorial 8. After server and path, we skip ahead and say channels, and provide an array of the channel or channels we want to read. So the array 0 reads only the left channel. Evaluate this, and we can verify B is, once again, a 1-channel buffer, and we have sound once again. So the takeaway here is mono buffers only. Using read channel and specifying channel 0 is a good habit to get into. All right, a quick bit of context here. We know what the original file sounds like, but what exactly are we hearing from GrainBuf? To unpack this particular sound, here's the source audio in a waveform editor, And 1/5 of the way through, well, that's the buffer duration divided by 5. That's about 1.38 seconds, which means our grain starts right about here and just shy of 1/10 of a second long. So if we zoom out a bit,
completely broke my.
We can hear it's the B at the beginning of broke my brain. So this is just to give us a sense of where we are in the file as we now turn our attention to these various GrainBuf parameters and explore how they affect the output sound, starting with this impulse generator, which is producing 10 grains per second. Relatively speaking, that's kind of slow enough at least that we can perceive the grains as individual events. So let's go ahead and press on the gas pedal a little bit. With grains produced at a fixed time interval using impulse, we can call this periodic or synchronous granular synthesis. And around 20 grains per second or so, the individual grains start to fuse together and we start perceiving a unified sense of pitch instead of the individual grains themselves. Using mouse X allows us to focus on that threshold more easily. Swap impulse for dust, and now we're doing asynchronous granular synthesis. We're still controlling density with the mouse, but ultimately the grains are randomly generated, so they never fuse together into a coherent sense of pitch. Instead, we just get a big noisy grain cloud that sounds kind of like making popcorn. All right, let's reset the trigger and move on to grain duration. If we increase the grain duration little by little, then we'll be able to hear more and more of the phrase, broke my brain. And it's very easy to notice that it gets louder. The rate at which grains are generated stays the same, but the grains are getting longer, which means there's more grain overlap. And when sounds overlap like this, their amplitudes get summed together, so in some cases we're likely to see higher peaks on the meters and possibly even clipping if we're not careful. So with high grain densities or long grains, you might want to compensate for the increase in amplitude by simply scaling the output, just like this. If we keep the grains long but lower the trigger frequency, we can get a sort of trance-inducing loop, kind of like this.
My brain. Broke my brain.
If the frequency of the triggers and the grain duration are inverse values, then each grain begins exactly when the previous one ends.
My brain. I had no broke my brain. I had no broke my brain. I had no broke.
And you can notice that with long, sparse grains, it becomes a lot easier to actually hear the bell curve shape of that Hanning envelope. So now let's go the other direction and start shortening the grains. And already we have a problem. The start position stays the same, but the duration is getting smaller. So our grains have gone from here to about here. And yeah, there ain't much going on in here. Under other circumstances, we could also have ended up here, or maybe here. So this is something to watch out for. Let's go ahead and nudge the starting position forward a little bit. So when the grains get really small, they basically become little clicks, each one maybe a dozen samples long. And the nature of the original sound they came from is totally concealed. What can we do with these? Well, for one thing, we can make buzzy tones by providing a trigger rate that's fast enough. And I know that doesn't sound like much, but we could make a stereo beating effect using multi-channel expansion and 2 slightly different frequencies. We also need to make sure to change this back to a 1-channel GrainBuf that can then be expanded to 2. And here's something interesting. By changing the grain size ever so subtly, we allow a slightly different chunk of audio into the grain. And so we're slightly changing the shape of this 60 hertz fundamental cycle. And when the waveform shape changes, so does the timbre of the resulting tone. Let's use mouse X again and also bring up a real-time spectrum analyzer alongside the scope. Instead of mouse X, we could automate this parameter with a noise generator, allowing the grain duration to kind of move around on its own, using multi-channel expansion here as well, so that the grain duration is unique in each channel. And just for fun, let's take this one step further, and instead of 2, we'll make 12 slightly different grain buffs, each with a unique grain trigger and unique grain duration, and spread them out across the stereo field using splay. That's nice. Now, like before, if we swap impulse for dust, our sense of pitch goes right out the window because the grains are no longer generated at a regular interval. And I guess let's go back to that simpler stereo configuration. With short grains that are more sparse, we're back to our crackly popcorn bits, but with a little more variety in the sound quality because the grain duration is changing. So that's basically how grain duration fits into the big picture. Let's reset to our original settings and move on to this grain start position value. As we've already seen, we can manually change this value between 0 and 1 to extract grains from different parts of the original file. But this doesn't need to be a static value. For example, we can make it completely random. Now in this case, we're generating 10 grains per second, but this LF noise is zipping around much faster, 500 random values per second. So how this works is basically whenever we get a trigger here, GrainBuf basically takes a little snapshot of this value. Wherever it happens to be at that moment, that's the location in the buffer where it grabs the next grain. So this is going to sound like some real gibberish. Now, there's nothing wrong with using 500, but it is a lot faster than we actually need. I think we could drop this all the way down to 10, the same value as the grain trigger frequency, and we'll get very similar results. But with a much lower frequency for this LF noise 1, and because this is a linearly interpolating noise generator, we'll be able to actually hear the grain pointers sort of slowly sliding around the file, which is kind of a cool effect. And same deal as before, we can very freely adjust the synchronicity, density, and grain duration for noticeably different types of effects. So this particular configuration with longer asynchronous grains will sound like this. And for another variation, we can make the grains much shorter and bring the frequency of the pointer randomness back up to 500. There are lots more interesting variations to explore, and you can pick something different here instead of LF noise 1, so I'll leave it to you if you want to continue experimenting. But let's say we don't want randomness. Let's say we want the grain pointer to move through the file from beginning to end. So for this, we could use a line that goes from 0 to 1, and the amount of time it takes to get there is determined by the duration of the buffer that we're granulating, so we can use BufDur. And when we get to the end, let's say we're done listening, so done action 2.
It just completely broke my brain. I had no idea what I was hearing
or that sounds like this could exist.
And all of a sudden, we can make sense of the whole phrase once again. But we also have this buzzy 40 hertz tone quality to it. It's got kind of like a robot voice effect going on. And this opens up some new possibilities. So first, let's gradually shrink the size of the grains and see what happens.
It just completely broke my.
When the grain duration was 0.01, the grains were big enough that our brains were able to get enough information to translate the sound into words, but small enough that they also have this clicky, buzzy flavor. But with these extremely short grains, that crispy, buzzy flavor is the overwhelming quality, and we can no longer really hear the content of the original file. Now, with longer grains, we lose the buzziness and start reconstructing the original audio file. And in this case, the ideal grain duration for a perfect file reconstruction is twice the reciprocal of the grain generation rate, which in this case is 2 times 1 over 40, which is 1 over 20. This means we get a very precise crossfade between adjacent grains, where each grain reaches its peak exactly at the moment that the previous grain fades out completely.
It just completely broke my brain. I had no idea what I was hearing or that sounds like this could exist.
To my ears, this is indistinguishable from just playing an audio file with PlayBuf, even though we are technically doing granular synthesis. Now, if we increase the grain duration beyond this value of 1 over 20, nothing interesting is going to happen. It's just going to get louder because we'll have more grain overlap and all the grains are perfectly in phase with each other. All right, let's spice things up. Let's say we don't want too much structure and order. Instead of a perfectly straight line from 0 to 1, maybe we want this line to, jiggle around a little bit as it makes that trip, but maintain that overall trajectory from 0 to 1. To do this, all we have to do is add a little bit of noise to the line, like we did before. But for the sake of consistency, I think it would make a little more sense if we express these values in samples and convert to a normalized range between 0 and 1 as the very last step. So our line is now going to represent a sample pointer from 0 to the last sample in the buffer, which has an index of the number of samples in the buffer minus 1. And the duration of the line stays the same. Then we're going to add a fast-moving noise generator with an output range of plus or minus 1,000 samples. Or here, if you prefer, you can specify a value in seconds and then multiply that by the sample rate to convert to samples. Last, because GrainBuf expects this value to be between 0 and 1, we take the whole thing and divide by the number of samples in the buffer.
It just completely broke my brain. I had no idea what I was hearing or that sounds like this could exist.
So it sounds just a little bit shaky, I guess. One way to conceptualize what's going on here is imagine yourself trying to draw a perfect circle with pencil and paper. It's obviously going to look like a circle, but it won't be a perfect circle. In this analogy, the noise generator here basically represents the amount of human imperfection in the drawing. And so if we increase this error little by little, eventually the noise completely overwhelms the line.
It just completely broke my brain. It just completely broke my brain. I had no idea what I was hearing.
Yeah, so with a deviation of a half second in either direction, that's like trying to draw a perfect circle in the middle of an earthquake. Now, a cool variation on this idea is to change the duration of the line, and indirectly, this affects the speed at which the pointer moves through the buffer from beginning to end. So for example, times 4 means it takes 4 times as long to get to the end.
It just completely broke my...
And if that's not creepy enough for you, we can also make the grain pointer move backwards by swapping the start and end values. All right, let's say we want to go from beginning to end, not once, but over and over again. Well, we're basically talking about sample looping. And as discussed in tutorial 8, we can't use line for this because line doesn't loop. But there are a few UGens that can do this relatively easily, such as LFSaw, Sweep, and Phasor. And for completeness, I'm going to show all three of these options as simply as I can. Okay, so LFSaw generates a pure sawtooth shape. It's just literally a repeating diagonal line from low to high. It's an oscillator, so it expects a frequency in hertz. So to achieve normal pointer speed, we need the duration of one cycle of LFSaw to be equal to the duration of the buffer. And because frequency and period have an inverse relationship, we set the frequency to be 1 divided by buffer duration. And since we're thinking in terms of samples, the range of LFSaw should be from 0 to the number of samples minus 1.
What I was hearing, or that sounds like this could exist, it just completely broke.
Notice that it doesn't actually start at the beginning, and that is because the default initial phase of LFSaw is 0, which causes the sawtooth to start at the midpoint of its diagonal segment, and that corresponds to the middle of the audio file. So to fix that, we provide a phase value of 1, which offsets the phase of LFSaw so that it starts at the bottom.
It just completely broke my brain. I had no idea what I was hearing, or that sounds like this could exist.
And from here, we can use simple multiplication to scale the frequency as desired in order to move the pointer faster or slower.
It just completely broke my brain. I had no idea. It just completely broke.
Sweep is a ramp that starts at 0 and by default counts the number of seconds that have gone by since the last time it received a trigger. So the idea is to re-trigger sweep every time a buffer duration's worth of time has elapsed. We can do this with impulse, running at a frequency of 1 divided by the buffer duration, just like we did with LFSaw. Now, the default rate of sweep is 1, but the technically correct thing to do here is multiply that by buff rate scale, just in case the sample rate of the original audio file is different from the current sample rate of the audio server. And if this sounds totally unfamiliar to you, I do cover this in tutorial 8, so I might recommend you go back and do a quick review of that one. Last, because sweep is counting seconds, and we're thinking in terms of samples, we need to multiply sweep by the sampling rate.
It just completely broke my brain. I had no idea.
And from here, we can continue scaling the pointer speed as desired by changing this number here.
It just completely broke my brain. I had no idea. It just...
Now, if that seems like an annoying amount of math for you, well, buckle up, because Phasor isn't that much better. Although I do think it's the UGen that's most clearly designed to be used for this purpose, and it's the one I usually go with because I think it provides the most flexibility. Phasor is kind of like LFSaw in that it's a repeating linear ramp from A to B. The first argument is the reset trigger, which I'm just going to put a 0 here and ignore it. Phasor automatically wraps back to the start when it gets to the end, so this is only useful if we want to manually re-trigger Phasor ourselves, which we're not going to do. Next is rate, and this is a per sample increment. By default, this is 1, which means Phasor is basically counting the number of audio samples that have gone by. Because we're thinking in terms of samples, I'm going to leave this at 1. But again, it's appropriate to multiply this by buff rate scale, just in case we have a sample rate mismatch. After this, Phasor needs start and end values. So we start at 0, end at number of samples minus 1. The last argument for Phasor is reset position. This is not relevant in this particular case because we're never going to reset Phasor ourselves, so I'm just going to ignore it.
It just completely broke my brain. I had no...
Once again, this value here is the one we want to change to make the grain pointer move faster or slower.
It just completely broke my brain. I had no idea. It just...
Whew, okay, that concludes the math segment of this video. I think that's probably enough pointer madness for now. So let's move on to grain playback rate, which is this value here. So we already know this is a ratio, so 2 transposes every grain up an octave.
It just completely broke my brain.
Classic chipmunk voice. And 0.5 is an octave in the other direction.
It just completely broke my brain. I had no idea what I was hearing.
And that is your basic demonic voice. But the interesting thing here is that we're shifting pitch without also affecting the total duration of the audio file. And this is something that we can't really do using basic sample playback techniques with like playbuff and buff read. Okay, so let's adjust a few things and see if we can't make this pitch shifting effect a little bit cleaner. For example, we might consider using a higher grain density and relatively long grains to kind of fill in all the gaps. And we should anticipate that lots of grains possibly means higher amplitude, so scaling back the amplitude is probably a good idea.
It just completely broke my brain.
It just completely broke my brain. I had no idea what I was hearing.
It just completely broke my brain. I had no idea what I was hearing.
And keep in mind, you don't have to think in terms of frequency ratios, which can be kind of clumsy. If you want to think in terms of musical semitones, you can do so and just use MIDI ratio to convert.
It just completely broke.
I think this actually sounds pretty decent. It's probably not the world's worst pitch shifter. It's probably not the best either. It's important to keep in mind that there's always going to be some degree of undesirable digital artifacts introduced into the sound when you apply a pitch shifting process like this, but it tends to be less severe if the amount of pitch shift is relatively small. If you've ever played around with pitch correction software, you've probably noticed that you can make small pitch changes and kind of get away with it without anyone noticing. But if you try to adjust by like several octaves, then the sound just becomes utterly ridiculous. Observe. No, that is not a useful sound. Now, there is one possible pitfall to be aware of. Suppose we eliminate this random pointer deviation by collapsing the range to 0. And so now let's play around with these rate values once again.
It just completely broke.
It just completely broke my. It just completely broke. It just completely broke. It just completely broke.
It just completely broke.
Weirdly, all of a sudden the sound has this strong ringing character. Let's swap this value for mouse X, which might make it a little easier to hear what's going on. Hey, it's me from the future. What I meant to put here was 0.5, 2, 1, but I mistyped and gave myself a linear range from 0.5 to 2.1 instead of an exponential range from 0.5 to 2. This barely has an effect on the sound and nothing's broken, but it's not what I meant to do. I guess I was just typing too fast.
It just completely broke my brain. I had no idea what I was hearing. But it sounds like this
Could exist.
It just completely broke my brain. I had no idea what I was hearing. It sounds like
This
could exist. It just completely.
It sounds cool and weird, but this is definitely not a good pitch shifting effect. It's just not good. Okay, it's a little tricky to explain what's going on here. It's the result of a few different things kind of working together, but basically we're having phase issues with overlapping grains. Now, if you've ever taken an audio recording class or maybe a musical acoustics class, you might have heard of something called comb filtering, which is a type of resonance caused by a regular pattern of signal interference, often the result of a signal being added to a delayed copy of itself. And that's basically what's going on here. There's grain generation rate, grain duration, the resampling factor resulting from the playback rate, and of course there's also the content of the original audio file to consider. And basically all these factors are working together to create a predictable pattern of phase-related interference between overlapping grains. As a result, certain frequencies reinforce themselves and other frequencies cancel themselves out. So in the end, we get these unique spectral colors with very strong resonance at certain harmonics. We can hear these clearly whenever the mouse is standing still, and moving the mouse causes the resonances to kind of sweep up and down, creating this kind of zipper effect.
It just completely broke my brain. I had no idea what I was hearing. But it sounds like this. It just completely broke my brain. I had no idea what I was hearing.
Or that sounds like this.
Could exist. It just completely broke my brain. I had.
Wild stuff. The point is, if you're aiming for a clean pitch shift, this tiny amount of randomness in the grain pointer can make all the difference, because even a tiny bit is enough to diffuse the phase issues and produce a noticeably cleaner sound.
It just completely broke my brain. I had no idea what I was hearing.
Or that sounds
like this could exist.
Similarly, you might find a slight improvement if you use dust instead of impulse for the grain trigger, because that removes the inherent fundamental frequency of the grain trigger. Because dust is random, the overall amplitude of the output signal might be a little bit less consistent than impulse, but I usually find this to be not too much of a problem, especially if you're generating plenty of grains.
It just completely
Broke my brain. I had no idea what I was hearing.
Or that sounds like this could exist.
It just completely
Broke my brain.
And with dust, usually, or at least in this case, you can actually omit the slight randomness in the pointer, and the pitch shift still sounds pretty good.
It just completely broke my brain. I
had no idea what I was hearing, or that
Sounds like this.
this
could exist.
But you can decide for yourself which version you think sounds best. All right, and now for something I hope you will find very entertaining. Let's use the horizontal and vertical mouse position to control pitch and time, independent of each other.
It just completely
Broke my brain. I
had
no
idea.
Oh, that sounds like this could
Exist. It just
completely broke my brain.
I had no idea what I was hearing.
Why that sounds like
this could exist.
Okay, well, that was fun. All right, these 4 parameters, grain trigger, grain duration, grain playback rate, and grain start position. I consider these 4 central pillars of GrainBuf. And if you can wrap your head around these, then you're basically good to go. Let's talk about this interpolation value for a second. This is what determines how samples are interpolated when the playback rate changes. 2 is linear, but if we drop it to 1, then the change in quality is subtle but definitely audible, particularly for downward pitch shifting. So here's my voice down about half an octave with linear interpolation.
It just completely broke my brain. I had no idea what I was hearing.
And again, with no interpolation.
It just completely broke my brain. I had no idea what I was hearing.
You hear the difference? Down pitching means the granulator is stretching out the waveform in the grains. In that case, it has to do some guesswork in between the original samples. And with no interpolation, it's just not guessing at all. So the resolution of the waveform degrades quite a bit, and there's a noticeable loss of quality that manifests as a bunch of high frequency garbage. So generally, I would not recommend an interpolation of 1. Now, if you want to go up from linear to cubic, well, personally, I cannot hear much of a difference in most cases. But the increase in CPU is noticeable. So for the moment, watch this first green number in the corner, the one right after the word server.
It just completely broke my brain. I had no idea what I was hearing. It just completely broke my brain. I had no idea what I was hearing, or that sounds like this could exist.
With linear interpolation, kind of hovers around 2%, maybe just below. And with cubic, it's up around 3%, maybe just below. Now that might not seem like very much, but if you've got a lot of granulation happening all at once, it can really add up. So pick whichever one you like best, but generally I think linear strikes a good balance. Panning is straightforward. We know how to pan. Since we specified 2 channels, this value here between -1 and +1 represents stereophonic positions, so grains toward the left, grains toward the right. And of course, we can also use a signal, noise generator, oscillator, whatever, to automate the pan position as long as we keep the output range between -1 and +1. Now for grain envelope, this -1 means we're using that built-in Hanning envelope. And with a configuration like this, we can very easily hear that bell curve shape. No idea what I was. Let's say we want to use our own grain envelope, something different, maybe a percussive shape with a very short attack and long release. The first step is to create an instance of env representing that shape, maybe something like this. So delete this plot message, call it E, and we load this env into a buffer. So we use buffer.sendCollection, providing the server and the envelope, but we can't just load an env into a buffer as is because these types of data are not compatible with each other. Buffers are discrete, envs are not. We need to convert the env into a discrete collection of numbers. And we can do that with the method discretize, providing the size of the collection, in parentheses. The default is 1024, and that's probably fine, but since we have such a short attack transient, I think I'd like just a little bit more resolution, so I'm going to go with 8192. Keep in mind, this does not actually have to be a power of 2. I'm just being a weirdo. So evaluate and plug it into GrainBuf right here. And now, we are applying our custom grain envelope to every grain. So that's GrainBuf in a nutshell. Now, before I conclude with a little creative example, I want to tie up a few loose ends. Number one, I've been using a mix of AR and KR UGens inside GrainBuf. Now, for example, earlier in the video, I used the mouse to control the frequency at which grains are generated, and I used an audio rate impulse generator, like this. Now, you might reasonably ask, impulse is controlling some aspect of GrainBuf. We're not listening to impulse directly, so can't we just use KR and save some CPU cycles? Well, yes, we can. Let's do it and see how that sounds. And let's compare that again to AR, which I think you'll agree sounds much better. At low frequencies, it's really not a problem, but when we get into higher frequencies, the low hundreds or so, KR just sounds kind of crappy. The grains are not perfectly synchronized, it kind of hiccups a little bit. This is simply because the control rate is not fast enough to provide the precise resolution that we're looking for with these fast synchronous grains. And this kind of problem might pop up with other parameters in GrainBuf as well, so the lesson here is, when in doubt, use an audio rate UGen, especially if it's a periodic generator running at a relatively high frequency. Number two, here's a question. Suppose we configure GrainBuf to produce grains that are each 2 seconds long, but they start 85% of the way through the file. In this case, that puts us at 5.85 seconds, which is right about here. This could exist just before could exist. There's only about a second of audio between that start position and the end of the file. So what happens? How does GrainBuf manage to conjure up a 2-second grain? The answer is simple. If GrainBuf bumps into the end of the file, it wraps back to the beginning and finishes the rest of the grain there, as we can clearly hear from this example. Could exist. It just could exist. It just could exist. So this is just something to be aware of, and a very good reason to make sure the ends of your original file are faded in and faded out, because if you're careless and clumsily hack off some important content, then all of a sudden there could be a huge discontinuity between the end and the beginning of your buffer, and that means some grains could have a big, ugly click right in the middle. Number three, negative playback ratios. Yes, you can do it, and yes, it results in grains being played backwards. But it's useful to know precisely how it works. To demonstrate, here is broke my brain over and over again. Broke my brain, broke my brain, broke my brain. And now let's flip the sign of the playback rate and play it again. As you might be able to guess, il-ilchma is not broke my brain backwards. Instead of extracting the grain and then reversing it, which would sound like this, GrainBuf starts at the start position and actually moves the pointer in the opposite direction, literally plays the file backwards. So what we're getting is the word completely, but backwards. Again, this is just a little nuance to keep in mind if you feel like messing around with negative playback rates. Number four, max grains, 512 by default. Like I said, this is a high ceiling that you probably won't hit unless you're actively trying to do so. Nevertheless, a very sensible question is, what happens if you go above the maximum number of grains? Does it crash the server? Does it blow up like a recursive filter? Fortunately, it does not. To demonstrate what happens, I'm going to make a somewhat dense texture and drop max grains all the way down to 12. So it sounds fine. It sounds like what I'd expect it to sound like, but the post window is clearly trying to get our attention. And just for emphasis, let's go ahead and drop max grains all the way down to 2. Obviously, there are too many grains. GrainBuf just won't create any new grains if it's already at capacity. It's kind of like a bouncer at the entrance to a club who is not letting people in because it is already ridiculously crowded inside. Last one, number 5. And this should be fairly obvious already, but keep in mind that your results will vary greatly depending on the type of source file you're using. So I encourage you to try granulating all sorts of things, not just spoken word, but recordings of instruments, synthesized sounds, ambient or environmental recordings. Drum loops in particular can have very interesting results. But regardless of what you choose, I think it's a good idea to just spin the wheel. Plug all sorts of numbers into GrainBuf and see what happens. Just make sure you're careful with your volume when using high grain densities or long grain durations. Now we finally come to the end, and since we've just been kind of casually goofing around with function.play this whole time, the last thing I want to do is show you a synth and some other bits of code that I've prepared ahead of time as a way of showing you what a more robust, polished example might look and sound like. Here's the synth, and although at a glance it looks quite a bit different, most of the differences are superficial. I've got a ton of arguments for the sake of flexibility, and one of the main differences is that instead of cramming all the details into GrainBuf, I declared several variables to represent GrainBuf's parameters, like density control, grain duration control, etc. One small upgrade I did here was to use select, so that I can choose either dust or impulse, depending on the value of this sync argument. Now I'm kind of thinking of sync like a Boolean here. So in other words, do I want synchronous grains? 1 for yes, 0 for no. And then that number is used as an index into this array containing dust and impulse. Dur control is simply a base duration value multiplied by a noise generator. So if I say dur rand is equal to 2, then the grains can be up to 2 times longer or 2 times shorter. Hey, me again, from the future. It's not really good practice to declare a synth argument named dur. In this particular case, it's fine, but if you want to use pbind to generate a sequence using this instrument, then there's no way to differentiate between dur, the synth argument, and dur, the delta time between events. What I should have done is give this a different name, like base dur, grain dur, something that isn't dur. If you watch tutorial 10, this will probably make a little more sense. Anyway, carry on. For position control, I've separated things out into multiple steps for clarity. We start with Phasor, which is our basic sample pointer that goes from beginning to end with an argument for speed. We add some noise, the amount of which we can control using pause rand, which is a value in seconds. We then divide by BufSamples to convert this to a normalized range between 0 and 1. And then finally, I've made one small addition, which is to add a base position value, which basically allows us to offset the pointer somewhere into the middle of the file instead of always starting from the beginning. Pan control has a base pan position plus some randomness and the ability to control the speed and range. We plug all of this into GrainBuf, we multiply by the envelope and amplitude argument, and that's it. Now, I've chosen default argument values specifically so that when we only specify the buffer that we want to granulate,
It just completely broke my brain. I had no idea what I was hearing.
we basically reconstruct the original sound with a simple 4-second envelope applied to the overall thing. But we can add a few custom values to recreate, for example, our very first example from the beginning of the tutorial. Bring the density up and the amplitude down to compensate. We get a drone. We can also specify the density as a MIDI note number converted to cycles per second if we want to think in terms of musical pitch. Going into asynchronous mode, we get popcorn. With pause speed at 0.25 and also adjusting density and duration to really fill in all the gaps, we get a time stretching effect. If we want to hear more, we can just increase the sustain time of the overall envelope.
It just completely
And we can independently add some pitch shifting into the mix.
Just completely broke.
Finally, here's my take on a slightly more creative example. You can pause the video, study the code, pick through the details at your leisure. But essentially, in summary, at the top, I've got a looping process that generates chords. Below that, another looping process that generates percussive rhythms. And at the bottom, a third looping process that's just being creepy and playing parts of my voice backwards and slowed down. And as you can see, there's a good amount of randomness sprinkled throughout the entire thing. That's it for tutorial 25. I hope you found some of this tutorial useful, and I hope you enjoy this musical outro. Thanks for watching. See you next time.
What are we doing? What are we doing?